we looked at the magnetic vector potential, we looked at the Ampere's law, and in the last class, we looked at the magnetic force. Okay, we looked at the magnetic force. We did an example of how the magnetic vector potential can be used to find the flux. And remember, magnetic vector potential is is very much used in the applications of antennas. Especially, so usually people, what they do is they try to find the magnetic vector potential near the antenna, and what will be the magnetic vector potential at the far field. They can easily do it using magnetic vector potential, and then from there they can find the magnetic field. We will look at this application in the antennas part. Okay. And then we looked at the magnetic force. We looked at the three types, how the magnetic force affects the charged particle in a magnetic field, which is moving with a velocity of u, which is Fm is q times u cross b. And if you have a current element, we can argue that a charge moving in a charge dq moving with a velocity of u is equal to nothing but I times dl. That is the current which is carried by the small elemental length dl. And then we can integrate and we get this as the expression for the force on a current carrying element under the influence of the external magnetic field. And we say extended that to the surface and the volume currents. And we took this example, and then we found what is the effect on this rectangular loop due to the presence of another current element, which is here. So to find the influence, or to find the magnetic force on this rectangular loop due to this current, we first found the magnetic field, which is external to this rectangular loop, and this is coming from this line current. So we first found the magnetic field, and this is that external magnetic field B1 for this current loop. And then what we found is we found the current, we found the magnetic force which is exerted by each of these small current lines, 1, 2, 3, 4, forming the loop. And we found that F1 and we found that, 2 and 4, you can evaluate. There will be a force on 2 and there will be a force on 4, but they will be equal and opposite in direction. And the force that we seen on the first loop is minus arrow. So what do you mean by minus arrow? As I have told you, if it is minus arrow, that means this is the direction of arrow, right? Because if you think this in a cylindrical coordinate, this is the direction of arrow. So if it is minus arrow, that means the force is in this direction. Now for F4, if you look at F4, F3, the force is in the positive arrow direction. So if you see here, F rho is now in the positive, in this direction. So this is the direction of F3, and this is the direction of F1. Okay, and then we found the total force F1, F2, F3, F4, which is equal to this one. So now what we conclude here, we conclude the following. See, if you have a current element which is carrying current in the upwards direction, and there is another current element which is also carrying current in the upward direction, see, upward direction, then the force exerted on this small current element, small, I'm not referring to only this part, this small current element due to this one will be in this direction. Similarly, for the current, the force exerted on this one due to this one will also be in this direction. So what does this means? The force which is exerted by the two current elements or current wires carrying current in the same direction is, so what kind of force is this one? Yes.
Attractive force.
Attractive force. So that means they attract each other. So two wires, if they are carrying current in the same direction, then they will attract each other. They will try to, say pull each other, try to pull each other. So this is because of the magnetic force which is exerted on each other. On the other hand, if we look at this one, this current element, which is carrying a force in this direction, whereas this current element is carrying a force in the upward direction. So what force is exerted by, this small current element 3 because of this current element I1? It is in this direction. So this is what F3 was. Similarly, you will also see that the force exerted on this one due to this one, although we did not calculate it because it is very difficult to calculate, but still we can generalize and say that it will be in this direction. So what kind of force is exerted on the two line currents which are carrying current in the different direction? This is a
repulsive.
It is a repulsive force. So this is the conclusion from this question, that if they are carrying current in the same direction, they will experience an attractive force. If they are in a different direction, they will experience a repulsive. Of course, as I told you, F2 and F4 will also exert a force. We did not calculate it. You can go and you can do it at home. Try to find the force which is exerted by this element 2 and this element 4. Try to see what is the force exerted. But this will be exerted either in the up direction or in the down direction. So it will neither be attractive nor be a repulsive force. Okay. So this is our magnetic force due to the external magnetic field part. Now let's move to our next topic. So that was the initial topic of our this chapter, where it is this chapter number 8, which is the magnetic force. See, if you see here, there are examples here for the charged particle as well, and this kind of example, similar kind of questions are there in the homework. So I would encourage you to just go and practice this. Okay, and then you have it for this one as well. We did a similar one in our class, and then this topic is not there it is not there in our course. It is excluded, magnetic torque. And now let's go to the classification of materials is also not included. Now let's go to the magnetic boundary conditions. So similar to our just a second, I did not open the lecture of 17. Okay, so now what is the magnetic boundary conditions? We will now derive the magnetic boundary conditions in a similar way as we did it for the electric field, because we have seen that in the electric field we were able to find two boundary conditions which are summarized here, right, for the electrostatics. First, from the conservation of electric field, we got that the tangential component of electric field is equal at the boundary. And then from the Gauss's law of electrostatics, we found that the normal component of the magnetic flux density at the boundary must be equal to the surface charge of that present on that boundary. This is what we found. Now, let's see how magnetic field will behave when it experiences a boundary. So here again we can start, and our starting point is what? Our starting point is the Ampere's law. So you can start with the Ampere's law. Ampere's law, which is the closed line integral h bar dot dl bar is the current enclosed. And from here, we can derive the relationship between the tangential component of the magnetic field. Okay, so this we are going to do here. So we are following the same analogy. See here, whatever we have it for electrostatics, we are following the same analogy. In the electrostatic, it is the conservation of electric field. In magnetostatics, it's the Ampere's law. From here, we got the tangential component relation, and here also we will get the tangential component relation. Then the Gauss's law of electrostatics, we got the normal component of the magnetic flux density relation. Here also we can get it. So this is the Gauss's law. So this is the Gauss's law of magnetostatics, which is closed surface integral b bar dot d bar is equal to 0. So if there was a charge, we got this expression. And if the charge is absent, then what we get? Yes. If rho s is 0, what we got? We got d1 normal is equal to d2 normal. Now here, using the same analogy, without even deriving, we can say that if this is equal to 0, that means b1 normal is equal to b2 normal. That is, the normal component of magnetic flux density is continuous at the boundary. So we got our first boundary condition. If you want, you can go and look at this derivation in the textbook, but it will be very similar to the derivation that we already did here. Okay, so now let's go and look at how we get the first boundary condition, which is H1 tangential is equal to the H2 tangential. So here again, the method is the same. So what does the method says? The method says that, how we did it for the electrostatics is the same. So we start with a boundary. So we take a boundary. So if you see here, this is my boundary. This is my boundary. This is my medium one. This is the boundary. Okay. And this is my medium one. So this is my medium one. And the green one is my medium 2. So these are the two mediums. And how the mediums are defined? We know it. The mediums are defined with the permeability mu1 and permeability mu2. So here we are concerned about permeability because we are looking at the magnetic field. Excuse me. So these are the two mediums. Now we are assuming, this is important, we are assuming that there is a surface current on the boundary. And this surface current is defined as K bar. Okay. Now we apply that, we put a small closed Amperean loop such that half the loop is in medium 1 and half the loop is in medium 2. Its height is delta H and its width is delta W. And these are the magnetic fields H1 in medium 1 and H2 in medium. Now we need to find the relationship between them. So let's apply the Ampere's law, very similar to how we did it in electrostatics. So the Ampere's law, closed line integral h bar dot dl bar is equal to I. Okay, so which I can decompose into 4 integrals. I can decompose into 4 integrals. First line, second line, third line, and fourth line is equal to the current enclosed. Now, what will be the current enclosed here, guys? The current enclosed will be only the current which is passing within your Amperean loop, which is this one. And how I can get this? I can get this by finding or by multiplying the component of my K bar, with this length. Go back to our, say, sheet. If you go back to our sheet, which is carrying a current I, see, if you remember, I showed you. So it is a sheet. And if this sheet is carrying current, some K, but this is the component of K, then how do you find the current? You find the current by multiplying this component, the component which is normal to this line. So Kn multiplied by length of this. So the length of it is, suppose if it is L, so it is Kn times L. This is what we did there. So we follow the same thing. So here the component is Kn, and what is the length from here to here, which is covered in the Amperean loop, is delta W. So that's why it is delta W. It should be small w, no problem. We can make this as capital W. So this is how we can find the current. So this is how we can find the current. So the current is Kn times L. And our Kn is a constant. That's why I can straight away multiply rather than going and using the integration. Kn is a constant. So this is what we got. Now, again, from our electrostatics, we are borrowing, and what we are saying that this component and this component, which is 1 and 3, because we want to evaluate at the boundary, so we will make this height goes to 0. So we make this height, delta H goes to 0. So when delta H goes to 0, the contribution from 1 and 2, will be 0. So 1 and 3, sorry, not 2, 1 and 3 will be 0. So therefore, what is left is only 2 and 3. So let's do it. So 2 and 3, H bar dot dl bar, because in 2, we are in this medium, so it is H1 bar dot dl. And in 4, we are in this medium, which is H2 bar dot dl is equal to Kn times delta W. Now, what will be H1 dot dl here? So I'm going from here to here. Okay. So if this is my delta W, so that means if I say that from here to here, so if I suppose this point as some point T, then this will be T plus delta W. Okay. So therefore, I'm going from here to here, which is T plus delta W to T times H1 T dot dt. Now here I'm not worried about X, Y, Z. Okay, guys. So I intentionally put, the Ampere's law, and we are trying to derive it in this way. I'm not considering any coordinate system. I'm working with tangential and normal components. See here, normal, tangential. So if red is my boundary, which is this one, okay, let me use the same color. If red is my boundary, which is this one, then anything which is residing here is the tangential component. This or this will be my tangential component. And my normal component will be the one which is going out. This is my normal. So that's why I showed here. This is the normal and this is the tangent. So based on that, I'm deriving. So this is because that's why I'm using this T and T. So T plus delta W to T, then H1. So if I do the dot product for H1 with this one, so I will take a small elemental length and this small elemental length, because I'm not using dx, dy, or dz. I'm using a tangential component. So this tangential component can be dx, can be dy. It is based on your problem statement. But here, I'm just saying it as dt. Okay, so H1, I'm now changing it to H1 tangential because this H1 bar I can decompose into two, right? So I can decompose into the normal and I can decompose into the tangent. So I can decompose into the normal component. So this was H1 normal and this is H1 tangent. So therefore, only this component, oh, sorry, just a second. So only H1 tangential, when you dot product H1, only H1 tangential component will exist because this is parallel to our line integration. So that's why it is H1 multiplied by D. Okay, so it should be D, not dot product. And this is H2 multiplied by D. This is a small correction. I will remove that dot. So this is the first one. And for the fourth, it is from here to here. So that is again from T to T plus W. T to T plus W, H2 T of dt is equal to Kn of delta W. And here, if you remember, I am taking into consideration the direction in the limits of my integral. Not here, in the limits of my integral. See, I've put limit L plus delta W to L. So the direction of my integration is taken care by the limits. So I'm not putting anything here, minus or plus, and I don't need to worry because I did not put the coordinate system. So I really don't know which one is AX direction and which one is minus AX direction. So in this case, I can just include the direction in my limits of integration. And that's it. So once you do this, you will get minus H1T delta W plus H2T delta W is equal to Kn of delta W, from where you will get as H2T minus H1T is equal to Kn. This is the required boundary condition. So again, in terms of statics, you know that this minus and plus of these depends on from where you are entering the boundary and from where you are going. So for example, if you are, so in this case, you are entering in from medium 1 and you are leaving medium 2. So it will be specific to this particular case. So we do not want that. We want to generalize. And therefore, as we did it for electrostatics, here also we generalize. So the generalized form is this one, which is AN12 bar cross product with H2 bar minus H1 bar is equal to the current, the surface current K. And here again, AN12 definition is the same as in electrostatics. That is, it is the unit vector normal to the boundary. So this is my boundary, normal to the boundary, and its direction is from medium 1. So whichever you select as medium 1, from medium 1 to medium 2. So in our case, this is medium 1 and this is medium 2. So medium 1 to medium 2. So this will be my AN1. And if you use this, you will get the same. Okay, so this is the second boundary condition. So in summary, we have two boundary conditions for magnetostatics, which is first is H1 tangential, this H2 tangential minus H1 tangential is equal to Kn. And second boundary condition is B1 normal is equal to B2 normal. That is, the magnetic flux density normal component is continuous across the boundary, whereas the tangential component of magnetic field is not continuous across the boundary because of Kn. So if you want for the special case where we don't have a surface current, then H1 tangential is equal to the H2. Okay. So now let's take an example. So now what is this example? This example is saying that we have a two semi-infinite medias. We have two semi-infinite medias. So we have two semi-infinite medias. Medium 1 occupies the region z is greater than 0. So let me put z as the vertical axis. So this is my x, y, and z. So z is greater than 0 is my medium 1. So this is my medium 1. If this is 0, so z is greater than 0 is here. While medium 2 is less than 0, which is this one. With relative permittivity, permeability, mu r1 is 2 here. This is my medium 2, and this is mu r2, which is equal to 6. Okay, and what is known to us? I know H1. So I know H1 bar is known to me, which is equal to this one. And I need to find H2 bar. And we know H1 bar near the boundary. That is just here, which is 0 plus. We know the H1 bar. And we need to find what is H2 bar near this boundary, which is 0 minus. Okay. So our medium 2, medium 1 is this, which is above z is equal to 0. And our medium 2 is this, which is below. And therefore, what will be our boundary? Which plane will be our boundary? Yes, Mr. Muhammad Al-Hazmi, can you tell me? So which plane will be our boundary here? Yes. So this is 0. Z is greater than 0. This is our medium 1. Z is less than 0, which is this one. This is our medium 2. So therefore, XY. Which plane?
XY.
XY, yes. So the XY is our boundary. So let me just draw it. So this will be our boundary. And just to make tell you that this 0 is staying in this boundary. So this is my boundary, XY. Okay. So guys, see, it's very important to visualize your problem, okay, to identify the correct tangential and the normal components. Because I have seen in the quiz that, some of the students, or I would say, more than, if I'm not mistaken, more than 40% of the students, they are unable to identify which is the normal and which is the tangential component. So therefore, visualizing is very important. So once we visualize, that's it. Half of the problem, I believe, will be solved. So once you visualize this, then I can now quickly decompose my H1 into the tangential and the normal components, because if XY plane is my boundary, then X component and Y component will be my tangential component, and the Z component will be my normal component. So therefore, I have now decomposed them. Now apply the boundary condition. So first we are applying the second boundary condition. Is easier, that's why. So therefore, B1 normal must be equal to the B2 normal. Okay. B1 normal is equal to the B2 normal. So therefore, mu naught mu r1 H1 normal is equal to mu naught mu r2 H2 normal. Put mu r1 mu r2 here and simplify. You will get that H2 normal magnitude is 16/6, which is 8/3. So therefore, the H2 normal vector will be 8/3 because it is in AZ. So it will be AZ. So we got the normal. Now we want to find the tangential component. For the tangential component, we can use this expression. And please, guys, don't confuse. This is same as the previous expression. See, in the previous expression, it was AN12 cross H2 bar minus H1 bar is equal to K bar. So this and this are same. If I move the cross product on this side, then I am swapping this. Here it is H1 minus H2. Here it is H2 minus H1. And if I move AN12 on this side, then this should be H2 minus H1. They are the same. Don't worry. Okay. Then what is unknown to us? H2 is unknown to us. So I will put H2 as it is. I will put H2 as it is. And then H1, I just put the complete, say vector, which is 5ax plus 2ay plus 8az minus H2 cross. Now, what is AN12? This is one last thing that we need to identify. Now, since we already know the boundary, what will be the AN12 vector for our problem statement? Yes, Mr. Hassan Al-Musallam, can you tell me? Mr. Hassan Al-Musallam, you are here?
Yes, I'm here.
Yes, so let's go, walk through together. So what will be the AN12 for our case? AN12 is what? It is the unit normal from the boundary. So this is my boundary going from region 1 to region 2. So the region 1 is the top of your blue plane, which is your yellow color. And
Yes.
2 is the bottom of your blue plane, which is the green color. So the unit normal to this plane will be going from medium 1 to medium 2. So it will be going something like this. So
Yes.
what is this in our problem statement? Which unit vector is this one?
Minus AZ.
Minus AZ. Okay. So therefore AN12 in our case is minus AZ is equal to K bar. Our K bar is given to us 3AX. So put the 3AX here. And now what we need to do is we need to simplify. That's it. This is the one. So if you simplify it, come see here. If you simplify it. Yes, Mr. Abdullah, tell me.
Dr. may you repeat how can you find the AN1 and 2?
Oh, you want me to repeat? Okay.
Yeah, if you don't mind.
Okay, sure. So how do you find AN12? See, according to the AN12, first you need to identify the boundary. So here we have already identified the boundary, that my boundary is the XY plane, where the Z is equal to 0, or origin is sitting on the plane. Okay, it is sitting on the plane. It is included in the plane. Now, according to the definition, AN12 is the unit vector. That its direction is, it is unit vector, which is normal to this boundary and moving from region 1 to region 2. So the top of this blue plane is my region 1, which is yellow. And the bottom of my blue plane, which is this green one, is my region 2. Okay. So first we need to identify this one. Now, once we identified this, then we can start. So let's start from this plane. Now, in my problem, I may, the problem says that this is medium 1 and this is medium 2. The problem has already told that to us. We do not need to assume. So therefore, the direction is from medium 1 to medium 2. So the direction is downwards. So therefore, from the boundary, you just go down, normal to this XY plane, go down and stop it. Now, after that, you just analyze. In our problem statement, what is this unit vector? If this is my X, this is my Y, and this is my Z, then this unit vector, which is representing this dashed blue arrow, is my minus AC. And therefore, I got it as minus AC. Clear?
Yes, doctor, thank you.
Okay. Then, khalas, after that, the things is very straightforward. So you get, to first, what you are doing here, your first cross multiply, you're doing the cross product with minus AZ. So AX cross AZ is AY, so 5AY. Then AY cross minus AZ, AY cross minus AZ is AX. Remember, so you are using this AX cross AY Okay, rather than putting it like this, let me put it in a circle because we know it. AX, AY, AZ, and this. This is the one. So AX cross AY is AZ, AY cross AZ is AX, and AZ cross AX is AY. You have to go in this map and then complete this. Okay. So this after, now I'm assuming that my H2 vector is this one. So it is H2AX plus H2AY plus H2AZ. So I'm now in place of H2 vector, I'm writing H2AX plus H2AY plus H2AZ. And where my unknowns are H2AX, H2AY, and H2AZ. H2AZ is not unknown to us. We know it, but you will see that the normal component will vanish because is now you have to cross product with AZ. So AZ cross AZ will become 0. So this will go. So AX cross AZ will be AY. So that's why you will get AY. Sorry, AX cross AZ, AX cross AZ, we are going in the opposite direction. So AX cross AZ will be minus AY. So AX cross AZ is minus AY. That's why you're seeing this minus. Then AY cross AZ is AX. So that's why it is AX and it is positive. Then AZ cross AZ is 0, is 3AX. So this is what we get in the next step. Okay. So here we are doing the same thing, and here we are again doing the same. So here we are making AX cross AZ is minus AY, but you already have minus AZ, so it became plus. Then AY cross minus AZ is minus AX, so that's why it is minus already AX, and this minus into minus will become plus. Then this is H2 times AZ, H2 cross AZ. Now after here, we just put our X component, unit vector AX and unit vector AY together. So this is the one, and this is equal to my K. Now let's do let's equate. So the components of the vector on the left hand side must be equal to the component vectors on right hand side. So therefore, is there any AX component here? Yes. So H2 minus AY should be equal to 3. So H2, where it is, I'm sorry, not AY. H2Y minus 2 should be equal to 3. So H2Y minus 2 is equal to 3. Then what about equating the Y component, AY component? Here nothing is there. So therefore, 5 minus H2X should be equal to 0. So therefore, H2X is equal to 5 and H2Y is 3 plus 2 is equal to 5. So therefore, my tangential component is 5AX plus 5AY. So once I know my tangential component and once I know my normal component, which is H2N is 8 over 3 times AZ, you can now find the total magnetic field H2 near the boundary, which is equal to this one. Okay, so this is how you have to solve. This is a little bit different than magnetostatics boundary condition because of the presence of the cross product. So it's better we do it in this way so that we don't miss out anything, because working with dot products is comparatively easier than the cross product. Now, this is another example where you need to repeat this example, but there is no surface current density because if the boundary is free from current. Okay, so this becomes very straightforward to you because first, nothing will happen to the normal component. And for the tangential component, what will happen? H1 tangential will become equal to the H2 tangential. So it is very straightforward. So it is 5AX plus 2AY plus 8 over 3. So nothing is going to happen here. So your H2 tangential will become same as your H1 tangential. Okay. So this is an example. Now, again, as we did it for the electrostatics case, here also we are doing the same thing. Suppose instead of vectors, if we know the magnitude and the angles of my a magnetic field in one region, then how can I find in the second region? So it's very similar that we did it for the electrostatic case. So here is an example where we are considering the the current free boundary. And if mu R1 and mu R2 is the permeabilities, and if I know H1, its magnitude, and the angle that it makes with the normal to the boundary, which is alpha 1, then can I find the magnetic field component in region 2 near the boundary and the angle it makes with the normal to this boundary, which is alpha 2. So we go and follow the same thing as we did it in the electrostatics, and it is completely based on the trigonometry. So if this is my H1, then I can find my H1 my normal component, and I can find my tangential component, right? So here also I can do the same thing. For my second boundary, I can find this one, and I can find this one. Okay, so what will be this one? This one will be, if I know the magnitude H1, if this vector magnitude is H1, then this will be H1 of sine alpha, right? Am I right? Oh, no, cos alpha, sorry. H1 of cos alpha, and this will be H1 of sine alpha. This similarly, this will be H2 of cos alpha, and this one be H1 of sine alpha. And now substitute. This is the boundaries. H1 tangential is equal to H2 tangential. B1 normal is equal to the B2 normal. So H1 tangential is equal to H2 tangential, which will be H1 sine alpha. This blue and this yellow, they are continuous around the boundary. So therefore, H1 sine alpha is equal to H2 sine alpha. And for the second boundary condition, B1 normal is equal to B2 normal. So B1, so that's why it is H1 cos alpha. If I want to convert it into magnetic flux density, I multiply it by mu naught, mu R1. But I'm discarding mu naught because the mu naught will cancel. So mu R1, H1 cos alpha is mu R2, H2 cos alpha. If I divide this, this is what I will get. And if alpha 1 is known to me, then I can find alpha 2. And once I know alpha 2, you can either use this or this to find H2. So it is very similar to our electrostatics case. Okay, so this is the magnetic boundary conditions. Now, these are the two special cases, and these are the special cases when we are talking about a boundary between a magnetic material and air, for example, a dielectric material. Because magnetic material, for example, iron, okay, its mu R value will be very much greater than 1. It will be mu R of iron is approximately equal to 5,000. And for the air, it is 1. So in such cases, how would be the magnetic field? So this is what here we are trying to see. Okay, and if you see here, if my medium is iron and air, and if my magnetic field is in the air, then as it enters iron, then it will enter almost parallel to the interface. Almost parallel to the interface. And the analysis is here. You can go through it. And now the other case, if my magnetic field is in the iron. Now from the iron, if it is going to the air, how it will go? So from the analysis, you will see that if it is in the iron, then it will enter air at almost 90 degrees. At almost 90 degrees. And remember, all our angles are with respect to normal to the pound. Okay, so these are all our the examples of our magnetic boundary conditions. Okay, and just one thing which I wanted to tell you guys, see, in our textbook, I think it is page number, yes. So if you see here, these are the material constants which are given to us. See, the material, the dielectric constant, that means which is the relative permittivity, and the relative permeability. So if you see, all our materials are classified based on the permittivity, permeability. These are the two things, and the conductivity. And the conductivity is also here. So we know it very well. Metals like silver, gold has very high conductivity, but insulators have very small conductivity. See here, it is 10 power minus 11, minus 12, and here it is 10 power 7. Similarly, permittivity, relative permittivity, it varies. See, it varies. It goes from 2, 3 to even up to 80 for various materials. And for the permeability, the relative permeability, we know it very well. Those who are non-magnetic materials, which are, the diamagnetic material and the paramagnetic materials. So these, they have almost mu r is equal to 1. And only those materials which are magnetic and classified as ferromagnetic materials, only those have very large value of the permeability. Okay, so this is how you can classify the materials. Okay, so I think just let's take a couple of poll questions and then finish it, and let me see how much information you have retained. Very simple poll questions, and after that we can conclude our class. Okay, so this is regarding the magnetic vector potential. Okay, so this is 40 seconds for you. So it says that why magnetic potential is a vector quantity in magnetostatics. Why we don't have a scalar quantity? What is the reason? So 20 seconds finished. 10 more seconds left, guys. 5 seconds left. 4, 3, 2, 1, and that's it. Okay. So let me share the results quickly. We have 43 and 46% here. What is the correct answer? Why magnetic potential is a vector quantity in magnetostatics? It is this one. We have 46% is the correct, because if we take it as a scalar, then we have seen that it has become restricted. The Maxwell's equations will be satisfied only in the region where the current density J is equal to 0, but you cannot apply somewhere else. And therefore, in order to assure that the magnetic vector Maxwell's equation, this satisfies in all cases, you are forced to have the magnetic potential as a vector quantity. And one is not at all correct, because working with the vectors is always bad compared to the scalars. Okay, now this is the last one. Just give me a minute. Stop sharing the results before finishing. Okay, so here comes. So again, say this is true or false. So therefore, only 30 seconds for you. So it says magnetic force on a charged particle Q moving with the velocity and under an external magnetic field is along the direction where the charge is moving. True or false? So you have 10 more seconds, guys. 5, 4, 3, 2, 1, and 0. So I think that's it. And what is the answer? So the answer is true. Yes, is it true? No, it is not true. I'm surprised. It is not true. Okay, we will look at it in the next class. Why it is not true? Because the magnetic force is always acts perpendicular to the plane of the velocity and the magnetic field. So it is not along the direction. Electric force is along the direction. Okay, so we will stop